a 10-minute buffer. What are you doing?
No one likes the red ones. Eat a red one.
Sure. Oh, for the winter. Either one of them would love it.
I asked you if I could give it to him, and then you were like, save it for her.
What's wrong?
I just said I got it when I wanted to do it for her.
Make all the news will pop up. Kyle, you're not early. You're right on time. So, for those that are watching at a later date, and those watching now, in the description are several links. There is a link, the first link is the main one that I'm going to be working off of. It is the maps for this initial lesson that I'm going to be doing. Then there's a second link in regards to Australia and the Western United States. The third link is going to be the challenge for my discrete math class. And then the fourth one is a website that I am going to be referring to called weddingseatplanner.com. I'll get there when the actual, when the lesson calls for it, let's just say. But anyway, let me give you the basics as to what this thing is about, and then we'll see where we can go with it. So this is what is known as the four-color theorem. Now, I'll give you the actual definition of it in a moment. Let me give you a little bit of backstory. In 1852, there was this guy wanted to color a map of England. There are all these different counties in England, and he was coloring them, and he wondered to himself, well, you know, what's the least number of colors that I could use where no two colors are sharing the same border? And he took this idea in question to his brother, who was working at university at the time, and they ended up publishing a paper on it shortly thereafter. And the theory, the idea, was within the parameters of the theorem that I'm going to write for you in a moment. The idea was that, well, at most, you will only need four colors to color any map, as long as the same color is not bordering itself. When I say bordering itself, obviously you know what it means for, let's say, a country or an area to border another area. I'll go into the details of that. If they just share a singular point, if you think four corners in the United States, that technically does not count as a border. But we'll deal with that in a little bit. Ultimately, this theorem, this four-color theorem, was proven in 1976 using computers. These guys basically figured out a finite number of cases. They figured out a finite number of cases, which actually was 1,938 cases of maps. It was really ingenious. And then they threw it all into a computer, and they had the computer basically color them by the parameters of the four-color theorem, and they basically proved it from there. This was controversial at the time because, well, mathematicians, they don't like it just to be like, well, the computer figured it out. They would like a bit more of an elegant proof rather than just brute force. Hey, let's just color all 1,938 cases and just make sure that it actually hits the procedures. You know, it's a really interesting concept. Hey, Joe is here. Hey, Joe. And Joe, guess what? I do have colored markers today. So, but, you know, we'll get to that in a little bit. Now, the theorem, the actual theorem of the four-color theorem basically comes down to this. Any map, parentheses, of contiguous regions. When I say contiguous regions, think of something like Michigan, for example. Michigan is broken up into two sections, so that's not contiguous. Contiguous just means that they're connected. But any map of contiguous regions can be colored with no more than 4 colors so that no two adjacent regions have the same color. This is the nuts and bolts of the theorem, and it's been worded in different ways and can be expressed in different fashions, but this is the nuts and bolts of it. You can color any map with 4 or less colors as long as no two adjacent regions have the same color. I didn't write the word same. Have the same color. There we go. So let me just give you an example. I'm going to draw something using the permanent marker, but then I'm going to color it in using the actual markers. So here is one particular example for you. So a map. Now again, this in real life you may not see an exact map like this with countries or states or whatever, but let's just say that's a noise. Let's just say that you have some kind of a map like this. And it is broken up into 4 regions. The 3 wedges on the outside and then the circle on the inside. Now again, no more than 4 colors. And we'll start with red here. Doesn't really matter which one we start with. But let's just make the center of this red. See how that turns out. It turns out nice. Yeah. And then we can make this one blue. Now again, if they share a border, you cannot be the same color, meaning that this one right here cannot be blue or red, so I'm going to make this one orange. And then, well, this region borders blue, it borders orange, it borders red. I have to do it in green, and this green is terrible. Let me get a different green. Yeah, it does look like the Google Chrome logo. I wasn't actually aiming for that. I wasn't aiming for that whatsoever, but it actually ended up accidentally being like that with the colors in different locations. There we go, much better green. Much better green. So you can see that this particular map, it absolutely needed 4 colors in order to fit the criteria of the same color not bordering itself. You had no choice, basically. Now, let's look at a different map. You could have a map that looks like this. Now, again, there are, let's see, there's 1, 2, 3, 4 regions within this map. I know it looks like a lock, but there are 4 regions within this map. And again, it doesn't matter which one we start with. Let's just start with one color somewhere. There's orange. And then, of course, well, orange can't border itself, so we'll throw blue in there. There we go. Now, this region is bordering both orange and blue, so cannot be also orange and blue. Put some green in there. There we go. Happy little green. And, well, that last region is bordering all three. It's bordering green, it's bordering blue, it's bordering orange. So this one has to be red. Now, the interesting thing about these maps is that, yes, these maps look completely different. And I colored them differently on purpose. I could have done a better job of that, but we'll deal with that another time. But believe it or not, here's the point. Both of these maps are technically the exact same thing. They both have the exact same type of mapping. I wrote the word map on top and I left my a little space off to the side. But you can convert each of these maps to look like a network of vertices and edges. In fact, and I'll show it to you like this. Now, I left the whatchamacallit, the circles open so that I could color them for a moment. But look at these connections. You have red right in the middle. And red has a connection to blue up top. Red has a connection to orange down to the left. And green down to the right. The map can be converted into this network where each region is represented by a vertice or a node. And the border, no matter how big or how small the border is, if they share a border, it is represented by an edge connecting those two together. And you can see, well, technically, every single country or every single region in this particular map borders everything else. Now, I said that they were exactly the same thing. Well, there's orange right in the middle. Here we go. There's orange right in the middle. And up top, it borders blue. This one right here. There we go. Gotta get my markers straight. Keep that over here for a second. It borders blue. Then you can clearly, so hopefully clearly see where this is going. But green was down here. Red was over here. And there's a bunch of, oh no, my camera. There we go. Hope I didn't break anything. Anyway, you can see a bunch of other connections as well. Blue is connected to green. Blue is connected to red. Red and green are connected along the side. It's the exact same type of map. This is how those guys in 1976 were able to boil all these maps down to only 1,938 cases. They did it because they realized that it doesn't matter what the map actually looks like. If they convert the map to a network, they realize that a bunch of these different looking maps end up looking exactly the same when you convert them to their network form. So if you do any research on the four-color theorem, you'll find that there are pages and pages and pages of these quote-unquote maps that are nothing more than networks. And they follow the exact same rules. Each vertice represents a region, and if it's given a certain color, every connecting vertice cannot have the same color. And according to the four-color theorem, you only need at most 4 colors, which is why I only have 4 colors here. There's no need for a 5th color unless you mess up. Unless you mess up. Now that's going to be the key, though. So let's see where this is going to take us. A couple of details in regards to the four-color theorem. A couple of details, and some of you may have missed it, but there's a star. edges cannot cross over each other. If I got a professional graphic artist to design you a logo, would you use it? Probably not. Only because I'd like to have creative control over that. I'd love to have creative control. But anyway, back to this. Edges cannot cross over each other. In fact, so just for the sake of argument, here is a network. This network cannot be made into a map because it cannot be untangled. I'm introducing this word untangled. This is actually a technical term that I'm going to go into a little bit more detail about in a moment. But if you're talking about this particular network, this network cannot be made into a map. It can't. Thus, it technically doesn't follow with the four-color theorem. I mean, yes, you could do 4 different colors, but I'll get into the details in a moment. The reason being is because of these two. I'll actually use my red marker on this one. These two edges. These two edges cross over each other. Now, there are some instances in which you can untangle a map. Right now, this map is what we call tangled. If I were to rewrite it, I could look at trying to untangle this mess by taking that red edge and trying to rewrite it like that, and trying to take the orange edge and, oh, can't do it. Can't do it. Can't do it. I can't untangle this map. I'm sorry, I should have been calling it a network the whole time. But since I can't untangle this network, this is not going to work. Edges cannot cross over each other. Another example would be something like this. This one's invalid too. This one, not a map. Can't be a map. There's no such map that would actually follow this particular design. Now, not only does this network, if you were to say, oh, well, you need 5 colors for this particular network, yeah, but you can't be a map with this one. There's no way that you can untangle it. I mean, yes, you could take this red one, and I guess you could, like a rubber band, you could pull it over here. And I could do it again with this orange one. I could pull it off to the side. But then if I try to pull anything else out, no matter what, it's going to be crossing over one of those other lines. I could pull this red one out to here. I could pull this orange one out to here. But then the other ones are... There's no way I can untangle it. These two networks cannot be made into a map because it cannot be untangled. The edges cannot cross over each other, just as a side note. So, some of the applications of this 4-color theorem, because I'm going to be going to some like visual pictures in a moment, which are just kind of fun for me. But some applications of the 4-color theorem are actually quite extraordinary. Imagine that you are scheduling like a taxi service, for example. Like I don't know, you have a run of like, you have control over 10 different Ubers or some junk like that. And you send them out on a task. Well, the first Uber that you send out, you cannot give them a second task to do until they have completed that first task. Those two tasks cannot overlap each other. Or, for example, and this actually goes for the wedding planning website. If you look at the descriptions, there's a wedding planning website. If you think about the connections that people have at a wedding, there's a lot of personal issues that come into play. Sally can't sit at the same table as John, and John can't sit at the same table as Mary, and Mary can't sit at the same table as Joseph, or some junk like that, whatever that ends up being. So if you make these connections using a map and then try to figure it out, okay, how do I configure their seating arrangement so that people are not sitting with people that they absolutely despise? Well, the four-color theorem again comes into play. It's one of those things where it doesn't have any practical application when they discover it, but then over the course of time they realize, oh wow, this actually does play into a lot of different areas of life. Here's another example. And now I'm going to be getting into some more weird examples in a little bit. But here's just, obviously a tic-tac-toe board example or some junk like that. Actually, do I have it already printed? Oh, I already have it printed. Yeah, since I already have it printed, I'm not going to use this. I'm going to use this. There we go. I prefer having it printed. So, obviously, there's no real map in the world that represents this, but, this could be like tables and seating arrangements and stuff like that. It doesn't really matter. But you could, if you wanted to, give this a shot. In fact, again, I would point out something very important here. Boom. This point does not count as a border. That point does not count as a border. Something like that does exist in real life. If you go to the Southwest United States, there are 4 states that they come to a point like that. That point doesn't count as a border. Now, I want to specify the point, because the edge does. These two border each other. These top 2 border each other. These bottom 2 border each other, etc. But this top right and this middle one do not border each other, because that point does not count as a border. Now, something that you could do, again, if you wanted to, I don't really feel like coloring all these squares in, but you could make these node connections like I referred to earlier. And instead of having this crazy looking map, you only connect where they share a border. And again, you don't make that cross in the middle because they do not share a border at that point. So this is a map with a network laid on top of it. And with that network laid on top of it, I can be like, well, I can color that in red. Since they do not share a border, I can color that in red, and that in red, and that in red, and that in red. And let's go Christmas. This one green, this one green, this one green, this one green. The 4-color theorem, again, I'm going to keep repeating it throughout the entire time, but the 4-color theorem, you need at most 4 colors, meaning there are maps that you can color with less colors, I should say. What's AFK? I don't know what that means. But anyway, back to me. Now, let's go a little bit more haywire with this thing. Away from keyboard. Okay, what? You guys are weird. Let's go more crazier. I like this example. So we have this example. Again, this map. Kyle, it doesn't have to be colors. It could be, you could represent each color with a number or a letter or something along those lines if you wanted to. Or some identification marker of some sort or whatever. But I'm looking at this and I have to color the whole thing with 4 colors. Now, again, it is possible to make a mistake. If a mistake is made and you're like, oh crap, I need a 5th color, well, you messed up. If at some point you need a 5th color, you messed up. The The four-color theorem states you only need at most 4 colors total, according to the rules of this thing. Now, mind you, this is in two-dimensional geometry, plane geometry, I guess they would call it, Plane, plane. If you go 3 dimensions, there's a whole different system to it, but I'm not going to deal with that. Let's start with this. Let's just make the middle red, just for the sake of needing somewhere to start. And then let's go green here. Now, again, I can't do green or red in these 2 spots. So let's do this systematically. I can't do green or red. I have to do a 3rd color here. Now, let's just see how long we can hold out with just 3 colors. Oh, yeah, Kyle, the Desmos thing, that's what it was for. It's supposed to be fun. I can actually see a bunch of your responses on the Desmos website, but that's another time. Let's see how long we can get away with not using a 4th color. This one, I can go green. Actually, I can already see that I need that 4th color, simply because of the way that this thing is generated up here. It's very strange, the way that thing's generated up there. Because, well, this one would have to be orange. Oh, no, but then this one could be red again. Yeah, let's do that. Let's see how long we can get away with this without using that 4th color. Let's see if we can't, you know, what the 4-color theorem is. I only need, at most, 4 colors. There have been people over the years that have tried to be like, oh, look, here's a map where you need 5 colors. Nope. That one can easily be taken care of. That one can easily be redone and turned into something where it only needs 4 colors. Now, you can probably see, looking ahead into this coloring, where I'm going to need that 4th color. Because I get to a point where this region is bordering green, red, and orange all at the same time. Here comes my blue. But that's the way it is. Now, obviously, if you wanted to make it a bit more artistic, you could plan out where your colors are going to be. But you absolutely need, at most, 4 colors to get this thing done. Let's look at a real-life example. A real-life example would be something like a map of Europe. Now, I have a backup just in case, but I printed it in a portrait. I prefer it in landscape. Let's look at a map of Europe real quick. Put that over here. Put that other map over there. But let's look at this map of Europe and put it in the center a little. Germany, Poland, Czech Republic, Slovakia, Austria, Hungary, Switzerland, Slovenia, Italy. You got to know your geography. But let's see how... Yeah, it's Eastern Europe, I know. No, it's not. Yes, it is. It's partially Eastern Europe. Trying to think. Yeah, because it doesn't have, like, France and Spain and England. It's part of it. Shut up, Kyle. Anyway. So, let's see how we can actually map this thing out. So, obviously, there's no singular points that are going to be connected here. This map isn't perfect. But, I don't know. Let's just start with Austria right in the middle. Austria, seemingly, I would say, is in the middle just because it borders a ton of different countries. And, again, let's see how long we can get away. Let's see how long we can get away with only using 3 colors. I could make Germany here orange. Oh, Germany. Deutschland. I can't make the Czech Republic or Poland orange, so I'm going to make Slovakia orange as well. I can't make Hungary, orange, Luxembourg. Luxembourg, I know, I know. You could also say, where's Vatican City? Where's San Marino? Where's Monaco? Like, again, I know my European geography, Kyle. Let's just deal with what we have here. Slovenia would have to be this color as well. And now I'm kind of stuck. I can't do orange here, and I can't do orange here, so I got to bring in my third color. Let's make the Czech Republic green. Let's make Hungary green. And let's make Switzerland green. Now, I don't have a choice. I have to make Italy blue. There we go, Italy. Now, just for the sake of the example that I'm trying to do here, let's make Poland red. Now, I want you to see something here. And this kind of goes back to what I was talking about earlier in terms of maps and networks. Look at these two examples side by side. Look at these two examples side by side. Now, you may be able to see it, you might not. But I'm going to tell you that these two maps are exactly the same. You are looking at identical maps. You are. If you think about it, look at the middle. Now, obviously, it's not to proportion, it's not to size, not to scale, but if you think of Austria being in the middle, bordering 1, 2, 3, 4, 5, 6, 7 different regions or countries, Austria bordering Switzerland, Germany, the Czech Republic, Slovakia, Hungary, Slovenia, and Italy. And then Poland being up top, just bordering those top 3 countries. I colored these exactly the same on purpose, just so you can see the network connection between the two. These two maps have the exact same network. They have the exact same network. Let me show you what I'm referring to. Now, instead of destroying my beautiful pictures right here, I'm going to draw this over to the side a little bit. Actually, I'll draw it to the side on both of them. So here's Austria, and I'll color them in a little bit, with a connection to the Czech Republic, to Slovakia, which make a connection there, to Hungary, which makes another connection down here, to Slovenia, which makes another connection here, to Italy, with another connection here, to Switzerland, with another connection here, to Germany, with another connection here, and another connection here. And then up top, you got a little Poland action going on, which connects to Germany, the Czech Republic, and Slovakia. They are exactly the same. I actually am going to draw this one in a few moments. But let me color in my network, just so you can kind of see how that works. Networks work a lot better in computers, because of the way that they can be mapped out using computer code. Maps are a little bit different on the other hand. Maps are made by life and times that formed them, whether it be natural land divides, oceans, what have you, border disputes. I love watching those videos that explain why certain places have a border the way that it looks. But yeah, this map and this network are congruent to one another. It's fantastic. Now, if I go back to this one right here, I will draw on top of it just to show you exactly what I'm referring to. I'll do the nodes on top of them, on top of each of them, because they're technically already colored. But Austria right in the middle, having those connections to each of them. each country bordering the next one like it's a bit of a wheel. And then Poland up top, connecting to all three. They're exactly the same. It's really fantastic the way this thing works out. The four-color theorem. It's not just a random guy just coloring maps anymore. It's a mathematical network that can be programmed. It's unbelievable. All right. Now, there we go. Obviously, with only, how many countries do we have? 1, 2, 3, 4, 6, 7, 9 countries here. And making a network with 9 countries is not that bad. It really isn't that bad. There's a couple right here. Now, in the links in the description below, you'll see there is a paper here that can be printed out in which, instead of actually coloring them in, you could kind of map it out first using a network and then color it in to make sure that you did it correctly. So I'll have to do this one on a separate piece of paper in a moment. But this one, if I were to do a connection here, these two have a connection. These two have a connection. It's also connected to here. You could label them if you wanted to by putting numbers into it or some kind of identification markers. Connection here with a little connection here. Let me just make sure that I got something going on. So this one only borders 2 of them. Good. This one borders 1, 2, 3 of them. Good. This one borders 1, 2, 3 of them. Good. This one borders 1, 2, 3, 4, 5 of them. 1, 2, 3, 4, 5. Good. This one borders 1, 2, 3. Good. And this one only borders 2. Good. So again, you could make a network and pre-plan what you're going to do. The fact that you're like, okay, let me see how many colors I need. Red. I can't do red here. I can't do red here. Let's do red here. And then I can't do red here, here, and here. Let's do red down here. And then let's try green. I can't do green here, but I can do green here. Ah, this one is only going to need 3 colors. Good. And then from there, you can take that network and be like, all right, I can actually draw this thing in now. If you're familiar with Sudoku, Sudoku is an advanced form of the 4-color theorem. It's a much more advanced form. And the reason why I say it's an advanced form is because, well, with a Sudoku, if you're familiar with it, using the numbers 1 through 9, you can only use them once in each row, once in each column, and once within each little 3x3 grid section. It's a similar notion to the idea that the same color cannot border itself. Oh wait, I was supposed to do another one that was green here. Yes. And then the rest are red. Excellent. I enjoyed Sudoku back in the day. It's enjoyable from time to time. It gets a bit monotonous. Sometimes it can get way too easy. That's why they have, like, competitions for Sudoku and whatnot. What do you call that? Oh, Joe. I don't even know if I want to know. I don't even know if I want to know. It doesn't matter exactly how many colors you use, as long as you use 4 or less. So, for example here, I had no choice. I had to use 3 colors. There was no way I was getting around that. But the 4-color theorem, again, that's why the theorem says at most. Joe, your jokes, they hurt my heart sometimes. Anyway. So, I'm going to do this one on a little separate piece of paper. I'm going to have to because I'm running a little bit out of room. So, with the western United States. Again, you can see it right here, these little four corners with Utah, Colorado, New Mexico, and Arizona. Know your geography. They share a point, but that point does not count as a border. Please keep that in mind. So let's just do this a piece at a time. I'll make this a little bit larger, and then I'll kind of transfer to the map over here. There's Washington, Oregon, and California. There's Idaho, Montana, North Dakota, South Dakota. I'm going to have to label these in a moment, but that's okay. Wyoming, Nebraska, Kansas, Oklahoma, Texas, Nevada, Arizona, New Mexico, Colorado, Utah. I think I got it. There, let me label them. There's Washington, Oregon, California, Idaho, Nevada, Utah, Arizona, New Mexico, Tejas, Oklahoma, Kansas, Nebraska, South Dakota, North Dakota, Montana, Wyoming, Colorado. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Good. Oh, I'm sorry, Shat. There were more questions. Could I have done the same after? Oh, yes. Sorry. Going back to Lily's question. She asked, could I have done that same map with 4 colors if you wanted to? Yes, you technically could have. And you would still be within the rules or the realm of the 4-color theorem. You absolutely could have. I guess the general rule that, not rule, I should say, not procedure even, strategy. Let's go with strategy. The typical strategy that people like to go with is, let's see if we can minimize the colors. Because if we attempt to minimize the colors, then somewhere down the line, oh, we might be put in a corner where we have to use a 4th color. So if you immediately go into it with, okay, I'm just going to use all 4 colors and then see what happens from there, you might accidentally fall into a trap of, oh crap, now I need a 5th color because I didn't follow a proper strategy or something along those lines. What's the difference between ooh and ah? I don't know. Anyway, back to this. So let's go state by state at a time. Washington, Idaho. Okay. Yeah. And then these are connected up here. Well, let's state at a time. So let's do Oregon. Oregon is connected here and here. I'm going to block Joe's comments. Let's see. Remove. And remove. Oh, there you go. Joe already, not Joe, Kyle already did them. Sorry, he timed him out. Anyway, back to this. Where is my head right now? Okay. Let me just, okay, I need to do this problem because I have so much more things. I'm sorry, not in terms of the lesson. I'm almost done with the lesson. My head is out there. I need to drink a cup of coffee. Okay. Oregon is connected to 1, 2, 3, 4. So 1, 2, 3, 4. Just got that. California is connected to just 3 states. Nevada and Arizona. Okay, good. So I got those 3 down. Let's do Idaho. Idaho is also connected to Montana and Wyoming and Utah and Nevada. Cool. I'm going through it systematically. Just so you know, state at a time, just to make sure I got all the connections done. Nevada is also connected to Utah and Arizona. Besides those other 3, 1, 2, 3, 4, 5. Good. Arizona is connected to New Mexico. Now, this connection right here at the corner does not count. That point does not count, but it is connected to Utah as well. Okay? Utah is also connected to Colorado and Wyoming, but not to New Mexico. That connection does not exist. Okay. Montana is connected to Wyoming and North Dakota and South Dakota. Got all those. Good. North Dakota to South Dakota. South Dakota to Nebraska. But Nebraska is also connected to Wyoming. Oh, hold on. North Dakota. North Dakota to Wyoming? Yes, connected. Got to go through it systematically. Okay. Nebraska is connected to Colorado, which is connected to Kansas. Oh, which is connected to Wyoming. All right, I did that. So hold on. 1, 2, 3, 4. Nebraska. 1, 2, 3, 4. Got him. Kansas. Oklahoma. Kansas to Colorado. Kansas is 1, 2, 3. That's it. Good. Oklahoma. Ooh, got that little panhandle thing going on here. Okay. It's connected to Colorado. It's connected to Texas. It's connected to New Mexico. Hold on. So 1, 2, 3, 4. 1, 2, 3, 4. Good. And Texas is connected to New Mexico. 1, 2. Good. I think we got it. This is a weird network. But these are the types of things that you'd have to do. Or that you could potentially do. It depends on how many things you have connected. So let's do it a piece at a time, see if we can't get it. Washington. California. Again, because I'm just going to try and minimize my colors here. Can't go Idaho here. I can't go Nevada here because it's connected. I can't go Arizona. I'd have to go Utah right here. Let's see. I can't go here. I can go Montana. There's a strategy thing going on. Can't here. I could do that one green. Again, they're going to be on that point, but that's still okay. I can't do those two. I could do this one with green. I can't do that one. I can't do that one. Yeah. My greens are done at that point. All right. Let's do blues. Blue. Connect, connect. I could do a blue here. I could do a blue here. I could do a blue here. Because they're not connected. I could do a blue here. And I could do a blue here. As long as they don't share a connection, I should be good. Let's try orange. And you can kind of even see right here, orange. I'm going to have to do a red down there, but we'll figure it out in a moment. I could do an orange here, and I could do an orange here. And I'm forced to use red. There are a ton of different ways that you could do this. There's a ton of different strategies that you could follow. But the way that this thing works out, again, you have to use 4 colors. Sometimes, like we did with Australia, you can get away with 3. You can totally get away with 3. And that's acceptable. It's perfectly fine. Let's just see what this... I'm not going to do the whole United States. I just want to color this little thing because I'm very excited that I actually got it to work properly. Know your geography. Anyone know your state capitals? You should know your state capitals. I'll do them one at a time. You got Olympia, Washington. You got Sacramento, California. You got Santa Fe, New Mexico. I'm just doing the green ones right now. Where am I? Kansas. Topeka, Kansas. Helena, Montana. Just looking at my greens. Salt Lake City, Utah. And I think that's all my greens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Good. Greens. Let's do blues. Salem, Oregon. Let's see. Phoenix, Arizona. Cheyenne, Wyoming. Oh, hey, Joe, you're back. Bismarck, North Dakota. Austin, Texas. My blue is running out. No, my blue. Oh, I royally screwed up. I royally screwed up. Did anyone see where I royally screwed up? I missed one connection. I thought I had gone through this thing systematically, but I missed one connection. Oh, sad days. Let's go back to this map real quick. There's a connection between Wyoming and Colorado. Right here. Chapow. Oh, no. Let's see if we can fix this. Let's see if we can fix this. Yes. We'll make this one orange. I'll recolor that in a moment. And we'll make this one red. Good. Ah, that would have ruined everything. Let's see. I can make this one orange. I can make this one orange. I can make this one orange. And yeah, I think I'm good. Oh, anyway, Boise, Denver, Pierre. Carson City. Lincoln. Oklahoma City. Nailed it. That was pretty solid. I thought that was gonna ruin me. I missed one connection between them. Man. See, the way these guys did it back in the 1970s using computers, they were able to prove the maximum number of connections that any country would have with another country. It's really fantastic. Now, you have that map. Now, you can do this on your own time, if you so choose. But I do also have a map of the United States. Now, the reason why I'm not going to do this one, he says check your email. Why am I checking my email? Word. Please don't do that, Joe. Please do not make a logo for me. But anyway, the reason why the map of the United States is a little weird is because of Michigan. Michigan, technically the little top portion of Michigan and the bottom portion of Michigan are separated by water. And according to the four-color theorem, they have to be the contiguous regions. And Michigan is not a contiguous region, which is why I was okay with coloring the western United States. But if I were to do something like this, it would really mess me up. So I'm going to say, if you want to give the United States a shot, that's up to you. But you don't have to, simply because Michigan would really mess you up. I mean, you can choose what you want to do with Michigan at that point. You want to consider them two separate regions. That's perfectly acceptable. Just be careful when you go about coloring it, because that could really mess you up. Now, for my discrete math students, in a few moments, I am going to be clicking and giving you an assignment. Now, this assignment is simply meant to be fun, okay? This assignment is not going to be a graded assignment, but I want to see what you can do with it. We're at home for Lord knows how long. School has been not canceled. We will not be meeting in person for the rest of this school year, unfortunately, obviously, based on the decision from yesterday. That's a whole other can of worms. But what I'm going to say, you have all this time at home. Maybe you're not working. Maybe you're bored. Maybe you've watched every single thing on Netflix. Who the heck knows? Here's my challenge. Look at that. Now, there are answers to this online, but this isn't the point. The point is not to look up the answer online. The point is to try it for yourself. And you could go into this just, okay, fine, I got 4 colors. I'm just going to start coloring. Okay, you could totally do that if you wanted to. However, you may run into like a problem. You may run into a little bit of a brick wall or something like that. You have to be strategic with how you go about doing this. Now, there was something similar to this online, I think, that I had that website for. But again, you're doing this one by hand. Basically, here's the strategy, I would say. Figure out what 4 colors you're going to use. Plan out maybe a few moves in advance. And just have fun with it. Just have fun with it. The little note at the bottom that I really love. This map was actually an April Fool's Day hoax in 1975. It was claimed that you couldn't do it in 5 colors. You had to use 5 colors, but that's not true. The 4 color theorem has been proven. And, it's just one of those things that you can make it look nice. You can try to make the design, like, pleasing to the eye or something like that. You guys have so much time at home. I can't even imagine, people crawling up the walls right now with just the insanity of not being able to, just live your normal life or something like that. I mean, yeah, I mean, they, I don't even know. Anywho. Now, Joe, in terms of a logo that you're trying to design for me, don't worry about a logo. My wife can design logos, but I don't need a logo. And if I was going to use a picture, I wouldn't use that picture. That picture, man, I don't even know what year that was. Yeah, I don't even want to think about what year that was. But no, I don't need a logo. Oh goodness, send me a picture that you want. No, I'm good. I'm good for now. I don't need a logo. But anyway, yes, and I should actually post that now to the Google Classroom for discrete math before I forget. Let me do that now. I have it saved in my drafts. Do-do-do. Da-da-da. Da-da-da. 1 second. Da-da-do. 4-color theorem, assign. Come on, computer. Do your thing. Assignment created. Excellent. Anyway. Well, yeah. That's the nuts and bolts of the 4-color theorem. There's a lot more details online for it in terms of what people use it for and just the funny things that go around with it. It's just one of those fun things in mathematics where it's like, man, how can coloring be turned into a mathematical problem? But it can. And it's beautiful and it's wonderful all at the same time. I don't even know. Anywho, that's it for me. I might be on later tonight in a non-math capacity. And you guys ever... No, some of you were here for last time. I've been speed running Mike Tyson's Punch-Out, but I'm getting I'm getting my time pretty good, so I might try to stream that tonight just for fun. I don't know. I'll be on the lookout for that. But anyway, I'm gonna end the stream here because I got some things to do, some things for school. But it's been fun, and I will see you guys on the next one.